So we know about limiting reactants and how they limit the amount of product that can be made, but what about those excess reactants and how much of the excess actually reacts to make the product? That's what we're going to find out today in excess reactants. How much is left over? By the end of this video, you should be able to calculate for the excess reactant that has actually reacted with the other reactant to produce the limited amount of product that's theoretically possible in a perfect world scenario. Before we jump into the excess reactant calculation, let's make sure that you remember and still understand the limiting reactant, because you still always need to find the limiting reactant first before you can figure out what the excess reactant is and therefore calculate how much excess reactant actually reacted. You're going to be pretty sick of the word react, reactant, reacted in this lesson. I promise you. So this review question comes from the previous lesson on limiting reactants. We're going to calculate the limiting reactant between 2 grams of Alka-Seltzer, and if I take 2 grams of Alka-Seltzer and dissolve it in 25 grams of HCl, that's hydrochloric acid, I can create salt, literally table salt, like the stuff you put on your French fries, for reals. So we want to figure out how many grams of NaCl can be made using 2 grams of Alka-Seltzer and 25 grams of HCl. Whenever we're figuring out a limiting reactant, you can automatically count on drawing 2 dimensional analysis magical lines to freedom. So let's go ahead and do that right off the start. Now that we have our magical lines to freedom drawn, we are trying to figure out the grams of NaCl that can be made. That's our goal. So let's put that at the end of our line. Grams of NaCl and grams of NaCl. We have 2 givens for 2-dimensional analysis lines. We have 2 grams of Alka-Seltzer and we have 25 grams of HCl. Whenever we see a dimensional analysis setup where we have grams of one chemical going to grams of another, we follow the predictable and same pattern every time. Given, molar mass, mole ratio, molar mass, answer. So let's go ahead and figure that out. We first need the molar mass of NaHCO3. Well, where do I find that molar mass? The periodic table, of course. And each Na weighs 22.99, each H weighs 1.008, each carbon weighs 12.011, and each oxygen weighs 16, and there happens to be 3 of those. So we're going to add up each of those values together to find the molar mass of Alka-Seltzer. My molar mass is 84.009. I'm just going to round that to 84. Now we can clearly see that the grams of NaHCO3 cancel, and I'm left with moles of NaHCO3. That needs to get converted into NaCl. That's my goal chemical. So now I need to use a mole ratio. Where do I find this mole ratio? We need to look at our balanced chemical equation. But wait, did we check and make sure the equation was balanced first? No, we did not. So before we go any farther in this math problem, we should definitely check to make sure our equation is balanced. When we balance a chemical equation, we need to compare the product side to the reactant side. Let's count up our atoms. We have 1 Na on each side. That checks out. We have 1 Cl on each side. That also checks out. How about the hydrogens? We have 2 hydrogens on the product side, and we have 2 hydrogens on the reactant side. Sweet. We've got 1 carbon here, 1 carbon there. That's all fine and dandy. How about the oxygens? We've got 1 plus 2 for a total of 3 on the product side, and 3 oxygens on the reactant side. So it is balanced. We're good. We can move forward with our dimensional analysis. Since everything in this equation is a 1-to-1 ratio, there's nothing that's 2 or 3 as a coefficient, we just need to plug in a 1 over a 1, which isn't going to change the math, but we still need to show how the units are canceling. So, for every 1 mole from the balanced equation here of NaHCO3, we have 1 mole of NaCl, which is our goal. So I'm going to put the goal mole on top. We see now that the mole of NaHCO3 cancels, and I'm finally left with the correct chemical, but not the right unit. So I need to convert my mole of NaCl to grams of NaCl using molar mass. Again, looking at our periodic table, we find that each Na weighs 22.99 and each Cl weighs 35.45. We just need to add those values together. Our final mass for NaCl, our grams per mole, is 58.44 grams of NaCl per 1 mole of NaCl. My mole of NaCl cancels. I finally have the correct units. We know we did it right. Now we can plug and chug into our calculator. We're going to take this 2 times 1 times 1 times 58.44, which gives me 116.88 divided by our 84 times 1 times 1, which is just 84. So 116.88 divided by 84 gives me a value of 1.39. So with 2 grams of Alka-Seltzer, I can make, theoretically, 1.39 grams of salt, NaCl. How about the HCl, the hydrochloric acid? Just like before, we need to find the molar mass of HCl. Each chlorine weighs 35.45, and each hydrogen weighs 1.008. If we add those two values together, we'll get our molar mass of hydrochloric acid. That gives us 36.458 grams of HCl in every mole of HCl. My mole ratio is now looking at HCl, which is still 1 because everything in the balanced equation is 1 to 1. So 1 mole of HCl. And now remember from the previous lesson about limiting reactants, everything from here is going to be the same here in the setup. So I'm still going to have 1 mole of NaCl on top. I'm going to have 58.44 grams of NaCl in 1 mole of NaCl. Let's make sure all the proper units cancel. Grams of HCl cancels, moles of HCl cancels, mole of NaCl cancels, and I am left with my goal unit, so I know I can plug and chug into my calculator. I've got 25 times 1 times 1 times 58.44. which gives me a value of 1,461 divided by 36.458 times 1 times 1, which is still just 36.458. So with 25 grams of hydrochloric acid, I can theoretically make 40.07 grams of salt. So between these two values, which one is the smaller? Hopefully you recognize that $1.39 is a lot less than $40.07. So this would be the smaller value, the smaller amount of product that's limiting the amount of product I can make. Therefore, the Alka-Seltzer, the NaHCO3, is our limiting reactant. By process of elimination, therefore, the HCl would be our excess reactant, our ER. So theoretically, in a perfect world, the maximum amount of salt we could make is 1.39 grams of salt. However, now we're interested in, well, if the max I can make is 1.39 grams of salt, and the limiting reactant gets used up entirely, and we know that HCl is excess reactant, how much truly excess reactant is left over? How much has not reacted? And how much has reacted of the excess reactant? Remember, I promised you'd be sick of the word react and reactant. I wasn't kidding. So let's think about this in a picture format first. So given this image over here with cars and tires, what reactant would be in excess? Hopefully you're recognizing that the 8 car bodies have filled up the tires that are present, and there's no more car bodies to finish using the extra 16 tires left over. So here the excess reactant would be the extra 16 tires in excess. But how did we determine how much excess there was? If you pause the video here, please take this picture to heart and think about it for a second. How would we have determined that there are 16 tires left over after this car assembly line is complete? Hopefully you recognized that each car requires 4 tires. I know it only shows 2 in the picture, but if you try and drive a car on 2 tires, good luck, buddy. So each car requires 4 tires, and there are 8 cars total. So 8 times 4 gives me 32 tires that have been used up entirely. If we started with 48 tires and we used 32, the way we get 16 is simply by subtraction. We would have to take our 48 minus 32 to figure out how many are left over that we could still use if we were to acquire more car bodies in the future. Likewise, when we find excess reactants in chemistry, we're going to end up doing a simple subtraction to figure out how much is left over. So we just found out that 2 grams of Alka-Seltzer could generate roughly 1.39 grams of salt, and 25 grams of HCl could generate roughly 40 grams of salt. And we need to know how much HCl actually reacts with the Alka-Seltzer in order to form the maximum theoretical amount of 1.39 grams. And then how much is actually left over of the 25 grams of HCl after it's done reacting. So let's go through the steps first. Step 1 is to determine which is the limiting and which is the excess reactant. So you're not going to get away from doing those two-dimensional analysis lines. As you learned in the previous video, you could either do this by figuring out the grams of the product of interest, or you could do it by option 2, where you can compare mole values to see how much is needed versus how much is given. However, I highly recommend just going with the grams option because you're going to have to do that anyways to figure out the amount of excess left over. Step 2, you're going to convert the given value of the limiting reactant, so whatever they gave you in the problem, to grams of the excess reactant. So now that you know which is which, you know which one's limiting, you know which one is in excess, you're going to take the given limiting and convert it to grams of excess reactant. So your goal is now grams of excess reactant. A simple grams to grams conversion. This will tell you the amount of the excess reactant that was used, that actually reacted with the limiting reactant. Step 3 is to then take the amount that was used, that you calculated in step 2, and subtract it from the given value, the total value of the excess reactant that you had to start with, just like we did with the car body tires. And after you do this third step, this subtraction, you'll figure out how much excess reactant is left over at the end, and also consequently figure out how much actually reacted with the limiting reactant. So let's continue with the same problem between Alka-Seltzer and HCl as we saw before. We already know that the Alka-Seltzer is the limiting reactant, and we already know that HCl is in excess. So let's jump to step 2. Step 2 is starting with our limiting reactant as our given, we are now calculating the grams of the excess reactant that's actually used, our HCl. So let's just plug in our values. As always, we're going from grams of one chemical to grams of another. That means we need our molar mass of NaHCO3 first, which we already calculated prior to, and found 84.007 grams per mole for the molar mass of Alka-Seltzer. We see that our grams cancel, and we need to get rid of the mole of NaHCO3 using a mole ratio. It's all 1-to-1 still, same chemical equation, so 1 mole of HCl, that's the goal mole, goes on top, and 1 mole of NaHCO3 on the bottom can cancel with our 1 mole of NaHCO3 on top. Now we need to get from mole of HCl to grams using our molar mass, which we also already calculated, 36.46 grams of HCl in 1 mole. Our 1 mole cancels. We are in fact left with grams of HCl. It matches, so we can just plug and chug into our calculator. So all we have to do is take 2 times 1 times 1 times 36.46 and divide that by 84 times 1 times 1. When we do so, our answer ends up being 0.868 grams of HCl. So that's the actual amount of HCl that reacted with Alka-Seltzer. So literally we had 25 grams of HCl to start with, but out of that 25 grams, only 0.868 grams of HCl actually reacted with all of the Alka-Seltzer. So there's going to be a lot left over, a lot of tires left over, if you will. So step 3 is to now just subtract, like we did with the tires for the car body example. We took the amount we started with and subtracted the amount that was used to figure out how much is left in excess. We know that we were given or started with 25 grams of HCl, and we know that 0.868 grams of HCl actually reacted with our limiting reactant. So 25 minus 0.868 grams gives us 24.13 grams of excess HCl, i.e. hydrochloric acid that's left over. It could still react with more Alka-Seltzer if we needed it to. Let's try this one together before I turn you loose and have you try one on your own. If we're going to consider the following reaction between magnesium and oxygen, making magnesium oxide, let's first balance it before we do anything. You should always balance or check for balancing the equation before you calculate. On the product side, I have 1 oxygen. On the reactant side, I have 2. Each side has 1 magnesium, so we need to balance the oxygens first. I'm going to put a 2 here in front of MgO. That 2 distributes in, and now I do have a balanced oxygen, but I have an unbalanced magnesium because I have 2 magnesiums here and only 1 here. So let's fix that and just put a 2 in front of this magnesium. Now we have a balanced chemical equation. Now let's read the problem. It says 0.64 grams of magnesium, I'm just going to write that on the top here, reacts with 1.2 grams of oxygen. And the question is asking me, what is the limiting reactant? Well, I need to figure out then how many grams of product is made based off of those two amounts of reactants. So let's draw our dimensional analysis lines. We have our magical lines to freedom, and we know that the goal is the grams of MgO that can be made. Now, if you're more comfortable with option 2 of figuring out a limiting reactant where you're comparing mole values, go for it. This is my preferred method, however, because you normally need to figure out how many grams are made anyways in order to get to the excess calculation as well. The first one has 0.64 grams of magnesium, and the next line has 1.2 grams of oxygen. We need the molar mass of magnesium from the periodic table, which happens to be 24.305. Let's plug that into our setup. Grams of magnesium per 1 mole of magnesium. And the mole ratio for this equation is not going to be all 1-to-1, so be careful, don't get in the habit of just jumping to that step. We need to look back at our balanced equation and see that for every magnesium there's 2, for every MgOs there's also 2. The goal mole goes on top, so I'm going to put 2 mole MgO on top and 2 mole of Mg on the bottom. Last but not least, I need my molar mass of MgO. Per magnesium is 24.305, per oxygen is 16. So adding those two values together, I get 40.305 grams of MgO per 1 mole of MgO. Let's double check and make sure all of our units cancel before we plug and chug. Grams of magnesium cancels here, mole of magnesium here, mole of MgO here, and we are in fact left with grams of MgO as our only unit. Excellent, now it's time to calculate. So we're going to take our 0.64 times 1 times 2 times 40.305, and that gives us a value of 51.5904 divided by 24.305 times 2 times 1. And that answer is 48.61. Now divide those two values to find our grams of MgO. And our final answer is, drumroll please, 1.06 grams of MgO. Or should I say, OMG, 1.06 grams. Let's do the bottom one now. We need to find the molar mass of oxygen. Each oxygen brings to the table 16 grams per mole, and there happens to be 2 of those. So 16 times 2 gives me 32 grams of O2 in 1 mole of O2. My mole ratio is going to be different than the one above because for every 1 oxygen, we have 2 MgOs. The goal mole goes on top. So my 2 mole of MgO will still go on top, but I now have a 1 here instead of a 2 from the previous equation. So 1 mole O2 goes on bottom. Now I need to have the molar mass of MgO, which is going to be the exact same setup as here from before, so I'm just going to copy it down below. I'm going to take my 1.2 times 1 times 2 times 40.305 to give 96.732 divided by 32 times 1 times 1, which is just 32. So when I divide those two, I get 3.02 grams of MgO. Whew! We're almost done with step 1, just trying to figure out which one is the limiting reactant. Comparing these two values, we look at which one's smaller. Of course, the $1.06 is smaller than $3.02, so my limiting reactant would be Mg. Magnesium is the limiting reactant here. So with magnesium being the limiting reactant, and thereby oxygen needing to be the excess reactant, we can make a maximum of 1.06 grams of magnesium oxide given these amounts of starting reactants. But wait, there's more! Now we have to calculate the grams of excess reactant left over. So we need to take our limiting reactant, the given amount, which happens to be 0.64 grams of magnesium, and convert it to a goal unit of grams of the excess reactant, oxygen. I've got a lovely little magic line, doo-dee-dee-doo. Third one, just for this one problem. Boom, boom, stoichiometry is the best thing in the world. Students hate it, but I love it, and it's useful, yeah. Oh, I've got the lovely little magic line. Doo-dee-dee-doo. So we're going to take our 0.64 grams of magnesium as the given, and I've now put my goal as the other reactant, the excess reactant, because I'm trying to figure out how much excess reactant actually reacted with the magnesium that got used up entirely. Because remember, the whole premise of the limiting reactant is that it's completely used. There's nothing left of it. You have drained its life dry by the end of the chemical reaction. So going from magnesium now to oxygen, we're just going to use very similar principles that we already calculated before. Molar mass, mole ratio, molar mass. The molar mass of magnesium from the periodic table and from what we saw before is 24.305 grams per mole of magnesium. And the mole ratio is 2 mgs for every 1 O2. So 1 mole of O2 goes on top because the goal mole goes on top, and 2 moles of magnesium goes on bottom. Now we need the molar mass of oxygen, which there's 2 of them, and we know that each oxygen is 16, so 16 times 2 gives me 32 grams of O2 in every mole of O2. Let's make sure all of our units cancel. Grams, grams, moles, 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 and we are left with the correct units. We know we did it right. We can plug it into our calculator. Hooray! So we're going to take our 0.64 times 1 times 1 times 32, and that gives us 20.48 divided by 24.305 times 2 times 1, which is 48.61. Once we divide those two values, we get 0.4213 grams of oxygen. So even though you started with 1.2 grams of oxygen, you only used 0.4213 grams of oxygen in order to completely use up all of the magnesium that's present. So this is the amount that was used in the chemical reaction. We need to figure out how much is left over. This is where our subtraction comes into play. If 1.2 grams was our start and 0.4213 grams was used, let's just subtract 1.2 minus 0.4213. And we find that that equals 0.778 grams of oxygen are still left over after the reaction is complete in excess. In other words, if we wanted to continue the reaction, we still have 0.778 grams worth of oxygen that could continue reacting with magnesium if we added more magnesium to the equation. Think you got it? We're going to go back to the same Alka-Seltzer and HCl balanced chemical equation and have you give it a try. How much NaCl is theoretically made, so still calculating for how much salt could be made, if we had 1.5 grams of Alka-Seltzer now and 8 grams of HCl. Also calculate the excess reactant left over. Go ahead and pause the video here and see if you can get the answer for this try it question. All right, let's check your answer. See if you set it up right and got the right answer. Ready? Go. Moving on to step 2. Ready? Hopefully you got step 1 correct and found out that Alka-Seltzer was still the limiting reactant and HCl was still the excess reactant. Let's move on to step 2. Ready? Go. All right, so after that calculation, we know that 0.651 grams of HCl was actually used when reacting with all of the Alka-Seltzer present, which was the 1.5 grams of Alka-Seltzer. Now we need to know how much excess is left over of HCl. We started with 8 grams of HCl, so 8 grams minus 0.651, which was actually used, gives us 7.34 grams of HCl that is actually still left over in the reaction vessel in excess. Hopefully you got that correct. And if you did, pat yourself on the back. If not, make sure you go back and check your work and see where you messed up specifically so that you don't make the same error in the future. In the next few videos, we'll also be doing some more practice and seeing if you really understand the concept of limiting reactants and excess reactants. But before we move on to some of the more fun application limiting reactant and excess reactant practice videos, please make sure you test yourself before you wreck yourself and give this problem a try. If you'd like to know the answer, make sure that you got it right. Please comment below. I'd be happy to let you know. Please give this video a quacks up, and I hope your day is just ducky.
No ducks, no glory.